A new, incredibly long-lived radioactive isotope of carbon had been found, one that could provide the key to unlocking the mysteries of biological pathways and the chemical underpinnings of life. Seldom has a single event so radically changed the course of human history. Particle physics has the ability to illuminate the dark corners of our universe and to drive humanity forward, but also the power to decimate, destroy, and leave us in darkness. When we think of the impacts of particle physics and nuclear decay, we think of huge machines like the Large Hadron Collider, seeking to understand the behaviour of our universe at the smallest scales, the wonders and dangers of nuclear power, and the weapons that changed our world in a flash. Today, I want to discuss another technology that fundamentally altered our world, a technique that leverages the high-energy particles smashing into our upper atmosphere from accelerators in the depths of space, as well as modern particle physics detection techniques, and the very biological pathways of the Earth's biosphere, to address some of history's greatest riddles, unravel how our sun's activity oscillates, and conclusively prove humanity's deleterious impact on the atmosphere of our only home world. We will discuss a technology that archaeologist Frederick Johnson nicknamed the atomic bomb of archaeology, a technology which appropriately rests on the pioneering work of a former Los Alamos scientist. Today we will discuss the brilliance, science, and monumental impact of carbon-14 dating. For seldom has a single discovery had such an impact on the thinking in so many fields of human endeavour. Before the middle of the 20th century, archaeologists had few ways to date archaeological objects. Objects had to hold dates or insignias, they had to have associated text records, or they had to show aspects of a particular historical style common to a known period. Creating a picture of the history of civilization and our wider planet was a testing, painstaking, and arduous task. Archaeologists relied on relative dating methods like stratigraphy and artifact styles to determine the age of archaeological finds. These methods could establish whether an object was older or younger than another, but not their precise numerical age. Chronologies were therefore long lists built up from and dependent upon historical relationships. They were tentative and often distrusted. However, in the 1930s and 40s, scientists were already researching radioactive isotopes that would largely obliterate this distrust and revolutionise our understanding of history. Radiocarbon dating revolutionised the field by providing the first objective, numerical dating method for organic materials, and it all depends on the radioactive isotope of a very common element, carbon-14. Carbon-14 dating allowed archaeologists to put together a history of humans across huge distances and from disparate civilizations all around the world. Suddenly, archaeologists could date numerous artifacts containing organic material, wood, charcoal, bones, and basketry. The dawn of radiocarbon dating upset archaeological chronologies around the world. Time and time again, objects and cultures proved to be older or younger than experts had previously believed. Carbon-14 dating unlocked the secrets of the Mayan calendar and how it relates to our modern calendar. It contributed to Western peoples acknowledging the ancestral history of Australian Aboriginal people that arrived in Australia more than 50,000 years ago. It debunked the claims of those who claimed to have discovered the shroud allegedly used to wrap the body of the biblical Jesus after his crucifixion. It has also allowed key transitions in prehistory to be dated, such as the end of the last ice age and the beginnings of the Neolithic and Bronze Ages. As anthropologist R.E. Taylor observed, carbon-14 dating freed archaeologists from the need to focus so much energy on determining the dates of their finds, and led to an expansion of the questions archaeologists were willing and able to research. Carbon-14 had a transformative impact on world prehistory by providing a universal timescale that transcended local, regional, and continental boundaries. However, this atomic bomb didn't just send shockwaves through the field of archaeology, it has also had monumental impacts in numerous other fields. It has allowed us to track the long-term changing activity of the life-giving sun. It has laid bare how our bodies, as well as the atmosphere, oceans, and land, absorb, assimilate, transport, and exploit carbon, even allowing researchers to track the age and progress of Alzheimer's plaques in patients' brains, as well as how tumours respond to chemotherapy. And it has allowed us to prove beyond any doubt that rises in the carbon dioxide concentration in our atmosphere are due to the burning of fossil fuels and the liberation of ancient carbon. The genesis and impacts of carbon-14 dating are astronomical. Carbon-14 dating has expanded human knowledge in so many ways and provided unparalleled insight into the history of human civilization. Now it is providing a stark warning for our future, a warning humanity must heed. The impact of this technology and the intricacy, subtlety, and importance of carbon-14 dating science is desperately underappreciated. That's something I want to help rectify. In part 1 of this mini-series, we will come to understand how radioactive carbon-14 was first discovered and isolated, and how scientists came to realise that rather than being a fleeting, ephemeral, short-lived isotope, carbon-14 permeates all organic material for millennia. It is a fascinating tale. In 1929, Ernest Lawrence, working at the University of California, Berkeley, developed an apparatus known as a cyclotron that used electrical and magnetic fields to accelerate protons to high velocities in a spiral-shaped path before they collided with a target. In 1930, Lawrence observed a curious aspect of his new atom smasher. If the nuclei of atoms are bombarded by beams of particles, the atoms of an element can be transformed into different variants of that same element, but with different masses and numbers of neutrons, so-called isotopes. Many of these isotopes then continue to emit gamma rays long after emerging from the collisions that produce them. They radioactively decay, some at rates low enough to allow the isotope to be isolated, contained, studied, and utilised. The potential value of a radioactive carbon isotope like carbon-14 was obvious long before it was first synthesized. Organic pathways depend on the flows of specific molecules, including hydrogen, oxygen, nitrogen, and carbon. During the 1930s, scientists hoped that a radioactive isotope of one of these abundant biological elements would be found to have a long enough half-life to be used for biological tracer studies. Being able to introduce a radioactive marker into and to track organic chemical pathways would revolutionize biology. Thus, early research into carbon-14 was focused on its possible utility in such applications, and not its ability to date historical objects. So how was this potentially revolutionary isotope discovered? Well, with many setbacks, much heartache, and not a small amount of luck. Yale physicist Franz Curie was the first to publish suspicions that carbon-14 could be artificially created. In early 1934, Curie used Lawrence's cyclotron at the Berkeley Radiation Laboratory at the University of California to bombard nitrogen with fast neutrons in a cloud chamber and observed the particle tracks created in the process. A cloud chamber contains a supersaturated vapour, usually of water or alcohol. The vapour is cooled to a temperature where it's ready to condense. So when a charged particle, like an alpha particle or electron, passes through the vapour, it collides with the vapour molecules, causing them to lose electrons and become ionised. The ions created by the passing particle act as condensation nuclei, and the vapour then condenses around these ions, forming tiny droplets that make the particle's path visible as a particle track. These tracks can then be observed and photographed to allow scientists to study the properties of particles and radiation. Curie observed that when nitrogen was exposed to fast neutrons, most of the time a short fat track was produced from the exposed nucleus. These tracks were those typical of alpha particles. Presumably the neutron was smashing into the nitrogen nuclei, ejecting an alpha particle and converting the nitrogen nucleus to one of boron-11. However, Curie also observed 6 anomalous and puzzling tracks. Occasionally, when the nitrogen nuclei were bombarded with fast neutrons, the nucleus spat out a very thin, very long track. Curie believed that these tracks were not the typical doubly charged alpha particles, but rather singly charged protons. He hypothesized that the usual alpha particle disintegration of nitrogen is accompanied by a much less frequent interaction where the neutron smashes into the nitrogen nucleus, causes the ejection of a proton, and converts the nitrogen into carbon-14, an as yet unknown isotope of carbon. Indeed, Curie's musings were the first suggestion in the scientific literature that carbon-14 might exist at all. And Curie's claims were met with huge skepticism by the scientific community. Curie's suggestion was radical. Physicists at the time assumed that the alpha particle was much the most likely nucleon to be ejected in such a nuclear reaction. The alpha particle is relatively stable. Indeed, alpha particles were considered to exist inside all appropriately heavy nuclei because of their relatively enormous binding energy per nucleon, and hence were likely to be emitted as single entities in nuclear reactions. In addition, the alpha particle was invariably the only heavy nucleon ejected when natural radioactive processes were studied. The idea that something other than an alpha particle could emerge in the disintegration of a nucleus was not taken lying down. In addition, scientists observed that even if Curie's anomalous tracks weren't alpha particles, the long thin wisps could have been formed by deuterons, composed of a proton and neutron, or even a tritium nucleus, composed of a proton and 2 neutrons. These interactions wouldn't produce carbon-14, but rather carbon-12 or carbon-13. Indeed, Curie himself accepted that these interactions were far more likely, as they produced nuclei of known stability. So, in 1934, few accepted that Curie had observed the production of carbon-14 in his cloud chamber. However, he had sown the seeds of a revolutionary new idea. Something other than an alpha particle can emerge when a nucleus like nitrogen-14 disintegrates. The next year saw a crucial turning point in the historical events that would lead to the discovery of carbon-14, and observations that would ultimately force physicists to reevaluate their basic assumptions about the disintegration of nuclei and nitrogen. In 1935, 2 different groups, Tom Bonner and William Brubaker of the Kellogg Radiation Laboratory at the California Institute of Technology, and James Chadwick and Maurice Goldhaber working at the University of Cambridge in the UK, independently reported that the disintegration of nitrogen-14 also occurred following exposure to low-energy, slow, or thermal neutrons. Chadwick and Goldhaber exposed tanks of nitrogen gas to beams of neutrons derived from a radioactive radon beryllium source in an ionization chamber. When the nitrogen disintegrates, the charged decay products ionize the gas in the chamber and produce an associated charge kick on a connected oscilloscope screen. Chadwick and Goldhaber then surrounded the source and chamber with paraffin wax to stop the fast neutrons coming from the radioactive source, and instead produced slow neutrons, which then bombarded the nitrogen gas. When the paraffin was added, the ionization kicks increased significantly. It appeared that slow neutrons were more easily captured by nitrogen nuclei, and therefore more likely to instigate nuclear disintegration. From the size of the ionization kicks on their oscilloscope, Chadwick and Goldhaber estimated that disintegration of nitrogen by neutrons should release about 0.5 mega-electronvolts of energy. In contrast, Bonner and Brubaker filled a cloud chamber with a mixture of water vapor and nitrogen at reduced pressure, and exposed the gases to neutrons from beryllium sources, with and without intervening layers of paraffin. If the disintegration of nitrogen is caused by a very slow-moving neutron colliding with a roughly stationary nitrogen atom, then the initial interaction happens roughly at rest, and with little initial momentum. This means that the disintegration products, assumed to be an alpha particle and a boron-11 nucleus, should fly out back to back to conserve momentum, and appear as a single straight track in the cloud chamber. Bonner and Brubaker observed just such tracks, including a group of tracks with a sharply defined mean range of 1.06 centimeters. And, just as Chadwick and Goldhaber had observed, Bonner and Brubaker saw far more of these tracks when their sources were screened with paraffin, and the nitrogen was exposed to slow rather than fast neutrons. However, Bonner and Brubaker then made a huge, false, historical assumption. They assumed that these tracks were a result of the standard nitrogen disintegration reaction, where a neutron kicks an alpha particle out of a nitrogen-14 nucleus, creating a beryllium-11 nucleus. Under this assumption, and based on the ranges the final state particles were able to punch through the gases of the cloud chamber, and Hans Bethe's range energy curves for charged particles, Bonner and Brubaker estimated that the neutron-instigated disintegration of a nitrogen nucleus released a significant 2.33 megaelectronvolts of energy. This value was significantly higher than the energy release values for the disintegration of nitrogen, calculated by Chadwick and Goldhaber in their ionization chamber. The difference was way beyond experimental uncertainties. So what was the source of this huge discrepancy? Goldhaber and another collaborator, William Bircham, believed they knew the answer, and it lay in Curie's tentative hypothesis that nuclei don't only emit alpha particles. Goldhaber and Bircham believed that Bonner and Brubaker had made a fatal mistake. They had assumed that the slow neutrons were causing nitrogen to disintegrate via the standard reaction. Nitrogen-14 plus a neutron results in a beryllium-11 nucleus and an alpha particle. However, Goldhaber and Bircham demonstrated that if the disintegration were assumed to take place with proton emission rather than alpha particle emission, and the production of a carbon-14 nucleus, then the energy release value associated with the interactions observed by Bonner and Brubaker reduced from 2.33 megaelectronvolts to 0.58 megaelectronvolts, a value in excellent agreement with Chadwick and Goldhaber's measurements from the ionization chamber. Here was strong kinematic evidence that the bombardment of nitrogen with slow neutrons produced a proton and the long sought after isotope, carbon-14. However, Goldhaber and Bircham went further. They wanted to prove once and for all that the disintegration of nitrogen by slow neutrons produced protons and not alpha particles. They wanted to distinguish between the two sets of final state particles. Bircham and Goldhaber therefore exposed two types of nitrogen-rich Ilford R emulsions to slow neutrons, R1 emulsion and R2 emulsion. Alpha particles are more ionizing than protons, and hence leave tracks in the R1 emulsion. The R2 emulsion is more sensitive, and therefore records ionization tracks from both alpha particles and protons. Following exposure, the R1 plate contained an order of magnitude less tracks, indicating that the disintegration of nitrogen produces far more protons than alpha particles. Scientists now had close to conclusive proof that the disintegration of nitrogen caused by slow neutrons produced protons and not alpha particles, and hence it also produced the isotope carbon-14. Nitrogen-14 plus a neutron makes carbon-14 and a proton. By the end of 1936, Franz Curie's initial suspicions, based on little more than long wisps in a cloud chamber, had been elevated to accepted scientific reality. The isotope carbon-14 could be produced in the laboratory. So, by the end of 1936, scientists were certain that carbon-14 could be produced physically. It had been discovered in the physical sense. However, scientists had no idea whether the isotope could be isolated and knew nothing about its properties or potential uses. The American historian and philosopher of science, Thomas Kuhn, remarked that the discovery of carbon-14 in a physical sense belongs in the expected category, but its discovery in the chemical sense does not. The chemical discovery of carbon-14 was still riddled with pitfalls. In 1937, Curie began working with physical chemist Martin Karman at the Berkeley Radiation Laboratory, with the aim of investigating neutron-nuclear interactions. Karman's thesis had examined 730 such interactions, and his observations were the same as those made by Curie. The neutron fluxes that early cyclotrons could produce were 10 to 100,000 times higher than those that could be achieved using standard radioactive sources, and by early 1937, Curie and Karman were producing thousands of slow neutron nitrogen disintegration tracks in cloud chambers connected to these revolutionary new particle accelerators. However, they still knew nothing about the physical characteristics of carbon-14, nor whether it could be isolated and studied. It seems certain that carbon-14 must be radioactive, and that it must emit electrons and beta decay to nitrogen-14. This conclusion followed from the observation that in no known element of low atomic number were there neighbouring isobaric pairs in which more than one member of the pair was stable. Examples of pairs with an unstable member included helium-6 and lithium-6, beryllium-7 and lithium-7, beryllium-10 and boron-10, and carbon-11 and boron-11. So scientists expected that for the isobaric pair carbon-14 and nitrogen-14, the stability of nitrogen-14 necessitated that carbon-14 be unstable. The rate of decay from carbon-14 to nitrogen-14 was also expected to be fairly high, as it was in one known analogous case, helium-6 to lithium-6, in which a nucleus with 2 excess neutrons decays to a nucleus with equal numbers of protons and neutrons. The common wisdom was therefore that carbon-14 must be incredibly short-lived, and an upper bound on its half-life of a few hours to a few days was postulated by Philip Morrison and J. Robert Oppenheimer. In 1937, scientists accepted that if efforts to isolate carbon-14 prove fruitless, that must simply mean that the half-life of the isotope is so vanishingly short that it disappears before it can be isolated. Although beta decay theory was in its infancy, and these predictions were far from ironclad, they were enough to stop Curie and Kármán from immediately seeking to isolate carbon-14, a pursuit that seemed doomed to failure from the start. However, in 1937, a new impetus was provided for producing and isolating radioactive isotopes. Ernest Lawrence, the head of the Berkeley Radiation Lab, became fascinated with the possibility of using neutron beams and radioactive sources for therapeutic applications. The new alchemy of radioactivity, science-based interactions that could transmute one element into another, might help realize one of the dreams of the ancient art: the banishment of disease. Indeed, after Lawrence convinced his brother John, a physician, to seriously consider the medical applications of neutron beams and radiating isotopes, the field of nuclear medicine was born, and radioactive isotopes of phosphorus, sodium and iodine were commonly used as tracers in biological research. As such, between 1937 and 1940, Kármán was tasked with designing beams, targets, procedures and protocols for producing radioactive isotopes that could be incorporated into and used to study biological systems and pathways. Kármán rapidly developed a dependable procedure for producing carbon-11, a relatively stable isotope of carbon with a half-life of 21 minutes. Boron oxide was bombarded with deuterons to produce carbon monoxide and dioxide containing carbon-11 nuclei. Plants were then exposed to the carbon dioxide and produced radioactive carbohydrates via photosynthesis. These radioactively tagged carbohydrates could then be used as tracers in metabolic contexts. During this research, Kármán regularly irradiated graphite targets with deuterons to produce the radioactive nitrogen-13 isotope for research into nitrogen fixation in plants. In May 1938, Kármán's colleague Sam Rubin observed that a number of these carbon targets showed no residual radioactive activity isotopic with carbon. Rubin's observations were lengthy enough that if carbon-14 had been produced in these blocks and had a half-life of 200 years or below, radioactive decay of carbon-14 should have been seen. This incidental finding underscored the commonly accepted view that carbon-14 must be an extremely short-lived isotope. And given that Kármán was working around the clock and had many research isotopes to produce, attempting to hunt down the unicorn that was carbon-14 was not high on his list of priorities. Indeed, Kármán was so busy producing radioactive isotopes that he was almost constantly contaminated with radioactivity. This made Kármán persona non grata around sensitive radioactive counting experiments. In late 1937, Kármán was assisting Philip Abelson with work on an ionization chamber, but the physicists were harassed by an irregular, drifting background signal. Abelson eventually realised that the noise was correlated with Kármán moving closer and moving away from the experiment. After forcing Kármán to strip naked, he demonstrated that the radioactive interference was coming from the front of Kármán's pants. By the middle of 1938, the demands for cyclotron time from biologists and medical clinicians was so great that the on-site cyclotron had to be run around the clock, and Lawrence began to seek funding from biological foundations and organisations to build larger and more powerful cyclotrons, citing preliminary positive results from neutron therapy and the use of sodium-24, phosphorus-32 and iron-59 isotopes in medical diagnosis. Meanwhile, Kármán and Robert Wilson began to design targets that could be placed inside cyclotrons, rather than being exposed to an external beam. These so-called internal targets could be subjected to much higher beam currents, increasing the rate of isotopic production and helping to keep up. This shift proved to be a key turning point in the isolation of carbon-14. As Kármán remarked at the time, obviously, the method of internal targets should find its most important application in the preparation of radioisotopes which are long-lived and difficult of activation, as well as in the demonstration of the existence of many radioisotopes as yet undiscovered. The ongoing search for funds to build additional synchrotrons met with some success in 1938 and early 1939, allowing 2 cyclotrons to run around the clock. However, Lawrence continued to push for more funding, citing ever-expanding neutron clinical data and the enormously developing tracer program made possible by Berkeley's 2 operational cyclotrons. Despite this expanding cyclotron program, Kármán and Rubin's own research on photosynthesis pathways was running into a dead end. Carbon-11's short half-life meant that there was limited time for plants to absorb carbon-11-rich carbon dioxide, produce carbon-11-rich carbohydrates, and then for the scientists to extract and analyse the molecules created before the activity of carbon-11 decayed away to incredibly low levels. Indeed, some of the analysis equipment Kármán and Rubin needed was at Stanford University, 50 miles away and along a busy road. Kármán and Rubin explored desperate measures, transporting their carbohydrates under police escorts, and Rubin even woke Kármán at 2 a.m. one night to suggest the use of carrier pigeons. Even when alternative analysis equipment was found to be operational 10 miles away at the Shell Oil Research Laboratories, there was simply no way that carbon-11 rich compounds could be transported quickly enough to facilitate suitable analysis. The carbon-11 tracer simply wasn't long-lived enough. At an incredibly depressing conference in September 1939, Kármán and Rubin realised that unless they could discover a longer-lived isotope of carbon, their research had run its course. Kármán therefore pitched one last desperate Hail Mary attempt to use an internal target technique to produce and interrogate carbon-14. Necessity would be the mother of invention. However, his pitch fell on deaf ears, as the targets Kármán needed were in constant use for the production of phosphorus-32 and iron-59 isotopic tracers. Kármán and Rubin were resigned to their fate, before an incredibly timely reprieve that would change the course of history. During Lawrence's most recent funding pushes, financiers had questioned the value of radioactive tracers in biological research, relative to the more rare but stable isotopes such as hydrogen-3, carbon-13, nitrogen-15, and oxygen-18. Berkeley had not been able to produce any long-lived isotopes of the biologically vital atoms hydrogen, oxygen, nitrogen, or carbon, and the funders were becoming restless. To attempt to head off their concerns, Ernest Lawrence informed Kármán that both Berkeley cyclotrons were to be immediately diverted to a round-the-clock effort to once and for all determine whether long-lived isotopes of hydrogen, nitrogen, oxygen, or carbon did or did not exist. Lawrence tasked Kármán with organising a complete and systematic campaign to determine whether or not long-lived isotopes existed for any of the elements in the first row of the periodic table. Kármán therefore drew up a comprehensive plan for every nuclear reaction deemed plausible with the projectile beams and target materials available. The plans initially targeted isotopes of carbon. Over the next year, Kármán and Rubin worked tirelessly to synthesize long-lived radioactive isotopes, but continuously met with failure. In January 1940, Kármán began what he called a Desperation experiment. He placed a graphite target inside the radiation laboratory's 37-inch cyclotron and exposed it to beams of deuterons, a hydrogen nucleus with an extra neutron, throughout the evening hours, over the course of an entire month. Kármán's hope was that carbon-13 atoms would absorb the deuterons, emit a proton, and produce significant yields of carbon-14. This experiment had been regarded as one of the most likely to produce carbon-14, but was performed in a spirit of mixed desperation and resignation, and involved a considerable degree of hazard from radiation exposure. The target consisted of colloidal graphite simply smeared on a copper backplate, and was not designed to withstand such long-term and intense particle bombardment, and the graphite was constantly flaking off. As such, Kármán had to examine the intensely radioactive probe nightly to ensure that some of the graphite still clung to the target surface. Occasionally, he found the irradiated graphite almost on the verge of falling off, and had to cement it back on with more graphite at his own peril. Kármán recalls that during this experiment, the weather was unusually violent, even for January, and on most nights the laboratory was subjected to heavy drenching rains and high winds. With hindsight, Kármán noted that the noise of the rain on the tin roof of the laboratory, accompanied by continuous blasts from high voltage discharges from the cyclotron, created an appropriate fanfare for the birth of a new long-lived isotope, one which was fated to occur during this bombardment. On the 15th of February 1940, after several sleepless nights and during a particularly violent storm, Kármán terminated the month-long exposure of the graphite sample. Shortly before dawn, he scraped the graphite, which now had the look and consistency of gravel, off the copper backplate and left the nuggets in a weighing bottle on Rubin's desk. He then headed home for some much-needed rest. At this point, one of history's most impactful scientific discoveries was almost derailed, when a red-eyed, unkempt Kármán was picked up and interrogated by the Berkeley police. The police were searching for an escaped convict who had recently committed several murders. Fortunately, witnesses cleared Kármán, who was released and continued to stumble onward towards sleep. As Kármán slept, Rubin found the sample on his desk and began to analyse it. He burned the graphite to produce carbon dioxide, and then bubbled the carbon dioxide through calcium hydroxide, lime water, to produce a precipitate of calcium carbonate, limestone. This allowed Rubin to ensure that any radioactivity coming from the sample must be coming from the decay of atoms that undertake the chemical reactions common to carbon, and hence from the decay of atoms that must be isotopic with carbon. When Sam Rubin placed his samples of calcium carbonate inside a Geiger-Müller tube, he immediately began to detect promising radioactivity. The effect was small and only 4 times above the background tick rate, but crucially, it was reproducible. When Kármán awoke later in the day, he telephoned Rubin, heard the exciting results, leapt out of bed and rushed back to the laboratory, where he produced a new probe target, this time one with graphite solidly bonded to copper. By February 27th, 2 weeks later, Kármán and Rubin had reproduced the initial results, ruled out any possible sources of background and contamination, and hurriedly wrote a preliminary account of their findings for publication. They were convinced that they had finally discovered and isolated carbon-14. However, much to their astonishment, carbon-14 was not an ephemeral, fleeting, vanishingly short-lived isotope. The half-life of carbon-14, the time it takes for half of a given amount of carbon-14 to decay, appeared to be anywhere from 1,000 to 100,000 years. Their initial estimate of 4,000 years was impressively close to the modern value of around 5,700 years. This amazing realization shed light on the reason for the negative results of previous years. Scientists had not been able to capture the radioactive decay of carbon-14, not because it was so incredibly fast, but because it occurred so incredibly slowly. They simply hadn't waited long enough. They hadn't had enough patience. They hadn't watched carbon-14 for long enough. Carbon-14 radioactive decays were hiding in the background count all along. They were hiding in plain sight. Carbon-14 decayed far more slowly than anyone had ever anticipated. That evening, Kármán and Rubin motored over to Ernest Lawrence's home to inform him of their discovery. Lawrence was at home attempting to banish a cold as he was due to receive the 1939 Physics Nobel Prize for the invention and development of the cyclotron the very next day. However, Despite these pressing distractions, Lawrence's enthusiasm for the discovery of carbon-14 was so great that both Kármán and Rubin were taken aback and immediately began to doubt their results. Fortunately, further experiments confirmed their initial suspicions. Carbon-14 had finally been created and isolated in a lab and had been shown to hang around for millennia. A new, incredibly long-lived radioactive isotope of carbon had been found, one that could provide the key to unlocking the mysteries of biological pathways and the chemical underpinnings of life. However, there was one last ironic sting in the tail for Kármán. Kármán's Desperation experiment had assumed that smashing high-energy deuterons into graphite was the best way to produce carbon-14 in the laboratory. That was to prove far from the case. Before Kármán had come preoccupied with his Hail Mary deuteron graphite smashing, he had set up 2 5-gallon carboys of saturated ammonium nitrate solution, acidified with nitric acid to remove any contaminating carbonates, and placed them in the deflector region of the 60-inch cyclotron. Here, the nitrogen-14 atoms in the ammonium nitrate were continuously exposed to both fast and slow neutrons. The success of the graphite probes had completely distracted Kármán's attention from those carboys, and he only remembered them when an angry group from the 60-inch cyclotron paid him a visit and demanded that the carboys, which had sprung hazardous acidic leaks, be removed. With no great enthusiasm, Kármán moved the containers to Rubin's laboratory in a ramshackle hut affectionately labelled the Rat House. Kármán and Rubin then decided to go through the motions and aspirate some gas from the containers, hoping that some carbon-14 might be present in the form of carbon-14 rich carbon dioxide. They passed the aspirated gases through calcium hydroxide and, much to their surprise, precipitated out a copious amount of calcium carbonate. To their astonishment, they found that even a small fraction of this precipitate was so active with carbon-14 radioactivity that it completely paralysed their radiation counters. The carboys contained a quantity of carbon-14 greater by 2 or 3 orders of magnitude than any they had seen in graphite probe bombardments. It seemed that the most efficient way to produce carbon-14 was hiding in plain sight all along. It was right there in the disintegration of nitrogen atoms caused by slow neutrons that Curie had mused upon all the way back in 1934. And it was right there in the same cloud chamber tracks Kármán had so assiduously photographed and studied in his doctoral thesis. Smashing deuterons into graphite targets hadn't been the way forward. Producing carbon-14 required a feather-light touch rather than a hammer. So, by 1940, scientists had discovered that carbon-14 could be synthesized using a particle collider and opened the door for carbon-14's use as a radioactive marker going forwards. Indeed, in 1944, Kármán and Baker published the first studies using carbon-14 as a biological tracer. However, given the pathway by which carbon-14 could be produced, it turned out that Mother Nature had already beaten scientists to the punch. This realization was to have staggering implications, not only for our understanding of biological systems, but also our tentative understanding of the past. Serge Korff was a Finnish-born American physicist and a pioneer of cosmic ray research. Cosmic rays are high-energy subatomic particles, mostly protons and nuclei, that are accelerated by astronomical phenomena such as supernovae, black holes and even the Sun, and which continuously smash into the Earth's upper atmosphere. In the 1930s, it was unclear whether slow neutrons, and hence carbon-14, could be produced naturally, at least in any significant quantities. In the late 1930s, Serge Korff, now at the Bartol Research Foundation at the University of Delaware, was trying to detect neutrons in natural radiation by sending Geiger counters on balloons to various levels of the atmosphere. During these experiments, Korff and William Danforth found increasing neutron intensity with elevation and suggested that this was the result of cosmic radiation smashing into the upper atmosphere. In December 1940, while working at the Franklin Institute in Philadelphia, Korff concluded that when cosmic rays smash into atoms in the atmosphere, they must liberate slower moving, slow or thermal neutrons. These thermal neutrons must then collide with the abundant nitrogen-14 atoms in the atmosphere, kick out a proton, and produce long-lived carbon-14. Just as Carmen and Rubin had observed earlier that year at Berkeley, Korff realised that the universe itself must create a vast quantity of carbon-14 in the Earth's upper atmosphere, and must have been doing so for millions of years. Carbon-14 might not only be produced in relatively small quantities in particle accelerators and cataclysmic astronomical events. Perhaps scientists were wrong all along. Perhaps we are surrounded by slowly decaying carbon-14. Perhaps all organic living material is saturated by the isotope. This study was the intellectual catalyst that seeded the revolutionary idea of carbon-14 dating. Given the natural production mechanism for the isotope and its incredibly long half-life, it seemed that carbon-14 might in fact be everywhere and every when. In the early 1940s, the world was embroiled with war. Scores of scientists were drafted into the Manhattan Project and tasked with beating Adolf Hitler to the creation of an atomic bomb. One of those scientists was Willard Wild Bill Libby. During this time, Libby became aware of Korff's research and insight and the potential ubiquity of carbon-14. And he realised that carbon-14 had the potential to reveal the secrets of global history. However, to understand how, you'll have to wait for part 2. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.